Inverse functions. In this chapter, we're going to talk about inverse functions and their properties. First of all, we're going to recall what we mean by a function. So a function is a relation between two sets where it assigns every element in the first set to exactly one element in the second set. So it's a relation between two sets where it assigns every element in the first set to exactly one element in the second set. So the first set is called the domain, and the second set is called the range. One-to-one function, again, a one-to-one function is a relation between two sets where every element in the domain has exactly one image in the range. So notice every element in the domain has exactly one image in the range. Another example of one-to-one. Now, why this one is a counterexample of one-to-one? Because 2 is related to B and 3 is also related to B. So this is a counterexample of one-to-one. This is not one-to-one function. Why we're studying one-to-one functions? Because only one-to-one functions have an inverse function. So if this is f, how we're gonna graph f inverse? So f inverse is gonna be from A to 1, from B to 2, from C to 3, and from D to 4. Let's bring back f. So notice the difference. F was 1 to A, 2 to B, 3 to C, 4 to D. Now let's look at the domain and range of both sets. So we can say the domain of f inverse is the same as the range of f, and the range of f inverse is the same as the domain of f. Keep in mind, this is just a notation of f inverse, and this is not the same as 1 over f. So this negative 1 here is the notation for the inverse. If I have a graph, how can I tell if it's one-to-one? We have a test called the horizontal line test. And if that line intersects my graph at one point, then the graph given is one-to-one. So let's draw a horizontal line to each one. So we can tell that the first graph and the last one has inverse function. And why? Because the horizontal line intersected my graphs at one point. Now let's graph the inverse of f of x equal to x minus 3. First of all, let's graph f of x. So this is a line with slope 2 and y-intercept is negative 3. Also, the function and the inverse are symmetric with respect to y equal x, which is a straight line that goes through the origin. So how we're gonna graph f inverse? We're gonna take 2 points on my first graph. So the first one we took is 0, negative 3. Now this point on the inverse is gonna become negative 3, 0. Let's take another point. This one is 1, negative 1. On the inverse is gonna become negative 1, 1. Notice how these points are equidistant with respect to y equal x. Now let's graph the inverse. So this is the graph of the inverse. Now let's graph the inverse of the cubic function. Again, The function and the inverse are symmetric with respect to y equal x, which is a straight line that goes with the origin. We took 3 points, and now I still need to graph. Now notice this portion here is going to be symmetric with respect to y equal x, so just flip it. And this portion also here is going to be symmetric with respect to y equal x. Therefore, this is the inverse. Another one. So we're going to take points on my function and switch the coordinates. So the first one was 1, 5. On the inverse is going to become 5, 1. Now 0, 6 is going to become 6, 0. Another one, 0, 4 is going to become 4, 0. And another one, negative 4, 0 is going to become 0, negative 4. And the last one, we have it as negative 3, negative 2 is going to become negative 2, negative 3. So how did we draw the inverse? We took the coordinates of the first one. We switched the x and y. Now these are the coordinates of, or the points that belong to F inverse. Properties of inverse function. We have the function and the inverse. Always their composition is equal to x. Now find the inverse of f of x equal to x minus 3. We have steps. The first step is write f of x as y. Then swap x and y. Then solve for y. We need to take it one step further. Now write y as f inverse of x. Let's verify that these two are inverses. So we're going to take their composition. So notice this is f inverse of x, and where did we replace that? In x, in f of x. Simplify. Therefore, we got x. Let's take it backward. Keep in mind this is f of x, and where did we replace it? In x, in f inverse of x. Simplify. Now we got x in both of them. Therefore, what can we say? That the function and its inverse are inverses. Another example. We need to find the inverse of f of x equal x cubed plus 6. So the first thing, we need to write f of x as y. Swap x and y. Solve for y. We need to take it one step further. Now write y as f inverse of x. Verify that these two are inverses. So keep in mind, this is f inverse of x, and where did we replace it? In x, where I see x in f of x. Simplify, we got x. So this is f of x, and we replace it in x in f inverse of x. Keep in mind, after we simplify the 6 and negative 6, we got x. So we got x in both of them. Therefore, the two expressions we have are inverses. Now let's verify that these two are inverses. We need to take their composition. So this is f of x, is 3x minus 7, but I need f of g of x. So take out x, write g of x. Now take out g of x and write the expression of g of x. Simplify. So notice the 3 kids simplify and 7 minus 7. So the final answer is x. So let's take the composition of g of f of x. So this is g of x, but I want g of f of x. So take out x, replace it by f of x. And now take out f of x, replace it by 3x minus 7. After simplification, this and this simplify, this and this simplify. Therefore, the final answer is x. So we got x. It means these two are inverses. Now we need to verify that these two are inverses. So we need to take their composition. So first of all, this is f of x, but I need f of g of x. So take out x, replace it by g of x. Now take out g of x, replace it by the expression it represents. We notice that after simplification, we didn't get x. So f of x and g of x are not inverses.